So our second law is Charles's law, and Charles's law was this idea that volume seems to be proportional to temperature. So this symbol right here just means it's a proportionality. So essentially as one goes up, the other goes up, or as one goes down, the other goes down. So whatever one does, the other kind of copies. And this was a very old gas law studied. In fact, if you've ever hot air ballooned, you've taken advantage of this gas law, because if you take the air in a hot air balloon and you heat it up to a higher temperature, it actually expands and takes up a bigger volume. So if this is air at room temperature, as you turn on the burner, it goes to a higher and higher volume, it expands. And of course, density is mass over volume. So if your volume goes up, then your density goes down, which means you tend to float in the air. And so if you cool down the air, it takes up a smaller and smaller volume. So you can do these experiments where basically you take the air or whatever the gas you're interested in, and if you measure the temperature here in units of, say, degrees Celsius, so room temperature is about 25, the boiling point of water is about 100, and there's only so cold you can get, but you see a very nice line that looks something like this. And actually, if you take a larger sample of air, it gives you a sort of a similar kind of plot. As you increase the temperature, the volume goes up, and as you decrease the temperature, the volume goes down. And a lot of people studied these, and what's really neat actually is if you take these lines, and there's only so cold you can actually get in the lab, and you go ahead and you keep drawing them, right, you get something that looks like that. And if I take this blue line and I keep drawing it, it looks something like that. And if you ask yourself, what's going on here? Does this make a lot of sense? If you look at the volume and you say, well, how big can the volume be? It can be as big as you like, I guess, up to the size of the universe. But as you cool it down, the volume gets smaller and smaller. And eventually the volume has to get to zero. And, zero volume means it's basically squashed completely flat. And if you go below zero, how can you have negative volume? And the answer is, well, probably not, right? So it probably doesn't make sense to go below this point here because the volume can't go below zero. And if you measure this temperature here, and people measure this temperature, it comes out to be approximately minus 273 degrees C. And this is thought to be the coldest temperature that's allowable in our universe. And because of this, we call it absolute zero. In fact, we introduce a new temperature scale, and we take the temperature in a scale called the Kelvin scale. And Kelvin is normally given the symbol K. Notice it's not a degree scale. It's not actually a relative scale. It's absolute. And we define it as basically the temperature in degrees C. And here's the clever thing, right? If your lowest temperature is minus 273, and you would think a scale where the lowest thing possible might be zero, you can achieve that by adding 273 to it. So you can take absolute zero and you can calculate its temperature. So if it's minus 273 degrees C and you add 273 to it, you get 0 Kelvin, not OK. And if you take something like 25 degrees C and you convert to Kelvin, you take your Celsius temperature and add 273 to it, and that gives you 298 Kelvin. And notice that we haven't used the degree symbol for at least 50 or 60 years here in chemistry. And if you were to take, say, 100 degrees C and convert to Kelvin, well, that's 100 plus 273, so that math's kind of nice. So that's 373 Kelvin. So our Kelvin scale is an absolute temperature scale, and we normally always use a capital T for our Kelvin scale, and we use a lowercase t for our relative, our degree C scale. So in all our gas laws, if you notice, I've written my T as a capital T, and that's because it's actually a Kelvin, an absolute temperature. So in Charles's law, we said volume is proportional to temperature. So as one goes up, the other goes up. And so it makes sense that if we divided one by the other, if they're both going up, then that rate of change should cancel out, and that gives us a constant. And we are assuming that our other things aren't changing. So we've got pressure, P. We've got volume. Okay, well, we're changing that, right? And we've got number of moles. Okay, so we need to hold it constant. And we got temperature. We're changing that. So we are assuming that pressure and number of moles are held constant in a Charles's law problem. And this allows us to write a useful equation. We can say, if you imagine a situation where you have a volume and a temperature, and you change one and you want to know what the other one is, so we can say V1 over T1, your initial volume, your initial temperature, and we go ahead and we change one of those, and so we can write on the other side V2 and T2. So we might know 3 of those, and we might be asked to solve for the 4th one. So let's go ahead and set up a problem here where we have to solve for, say, I don't know, how about the final temperature? So what would be a problem like that? So we can take, for example, we're feeling pretty happy, so we can take 5 milliliters of laughing gas. Why not? And it's got a temperature of, say, 25 degrees Celsius. And we are going to go ahead and cool it down. And so we're going to cool it down until the volume is, say, I don't know, 2.0 milliliters. And the question might be, what temperature is this equal to? So we want to know how cold we have to take our laughing gas and cool it down to until it only takes up 2 milliliters. And of course, one reason we might be interested in a problem like this is that most gases take up less room the cooler they are. And so if we're transporting gases around, the colder it is, the less room they take up, so the more gas we can transport. So we can take our Charles law equation here, V1 over T1, and we can go ahead and say, well, V1 is our initial volume, that's 5 milliliters. T1 we got to be a little bit careful of because we're given the temperature in degrees C, and we need to convert that to Kelvin. So we remember that we can just take the Celsius temperature and add 273, and that gives us 298 Kelvin here. So this is our capital T1. We should go ahead and check what we have. And we're asked to find T2, so I guess that's our question mark here. And we've cooled it down to the volume is 2 milliliters, so that would be our V2. So we have everything in this problem except for T2. And this is a sort of a standard math trick. So how do we get T2 by itself? Well, there's a couple of different ways to do it. I think probably the easiest way is just to cross multiply, and that is you can take the bottom of one side and crisscross it up to the top of the other side. We're really just going to multiplying both sides by the denominator if you want to see what we're really doing. And so that allows us to write V1 times by T2, which we brought up across to the other side, is T1 times by V2. And how does that help us? Well, we know V1 and we know T1 and we're told V2 and we want to find T2. And so in order to find T2, we got to get it all by its lonesome self. That means we've got to divide both sides by V1 in order to have those V1s cancel out. So we did this because now we've got T2 on the top, and that is equal to T1 times V2 over V1. So we can plug it in. So T1 is 298 Kelvin. Always remember, if your temperature is capital, that means it is in Kelvin. So don't forget to change your degree C to Kelvin whenever you can. And what else do we have? We have V2, which is 2 milliliters. Notice we don't have to convert to liters or anything. V1 on the bottom is 5 milliliters. And the reason we didn't have to convert both of those to, say, liters is that whatever you have on the top and the bottom, those units cancel out. You could have divided both of those by 1,000, but when you divide them by each other, those thousands just cancel out. And so we can go ahead and we can plug in now. And when I do that, I get 119.2. And what are my units here? My units here are Kelvin because my milliliters have canceled out. And I need to convert that to a temperature. And maybe I want to know that in degrees Celsius. So how do I get it in degrees Celsius? Well, I add 273 to get degree C to Kelvin. So I subtract 273 to get Kelvin to degree C. And that gets me minus 153.8. And if I ask myself, right, how well do I really know this stuff? Well, if I look at the significant figures, 298 is 3, 2 milliliters is 2, 5 milliliters is 2. So I probably only know this temperature to 2 significant figures. So that means that I can probably only really write minus 150 degrees C. So that's pretty darn cold, right?